All right, we're going to really change directions here from our previous material, and we'll start by talking about dot products. So what is a dot product? Well, definition is if you have two different vectors, u and v, and they both have n entries, it's a scalar quantity, and we denote that scalar quantity by u dot v, and what that's equal to, it's u1 times v1 plus u2 times v2, all the way to adding un times vn. Right, so we're multiplying corresponding elements in the vector, then adding them all up. So here's three examples. This would be a good spot to stop the video and see if you understand the definition first. Right. First example, right, multiply corresponding elements and add them up. So negative 14 is the dot product between those two vectors. Next example, multiply corresponding elements and add them up. You happen to get 0 in this case. This would be 2 plus 6 minus 8, 0. In the last example, each vector has 4 elements, so we need to do 4 multiplications, and then add them all up, and you get 30 in that case. All right, using this idea of dot products, we can talk about the length of a vector. So the length, which also you can use the name norm or magnitude, they all mean the same thing. So the length, norm, or magnitude of a vector that has n entries, so this vector lives in Rn, right, n-dimensional space. We denote that by 2 bars around the vector, so 2 bars on each side of the vector, and so that just means the length of that vector, and the way it's defined is it's the square root of v dot v. Right, so you dot the vector with itself to get a scalar quantity, and then you take the square root of that scalar quantity. So an example of length of a vector is if we're trying to find the length of the vector 3, 4, well, you do the square root of the vector dotted with itself. So 3, 4 dotted with 3, 4. Well, that'd just be 3 squared plus 4 squared. You take the square root, and that's 5. If we're trying to visualize this, right, we already knew from our previous geometry that from Pythagorean theorem, that length should be 5 because the base of one of the triangle is 3, and the height of the triangle is 4. When you think about this vector as a triangle, and 3 squared plus 4 squared is 5 squared, so the length of that hypotenuse is 5. So it matches up with our previous knowledge. All right, another example, length of a 4-dimensional vector. Well, dot that vector with itself and take the square root. Well, it would be 1 squared plus 2 squared plus 3 squared plus 4 squared, which is 30. Then we take the square root, and so square root of 30 is the length of that 4-dimensional vector. Well, sometimes it's convenient to do what's called normalizing a vector. What does that mean? Well, first, if v is a unit vector, what we mean by that is the norm is 1. The norm of that vector is 1. Remember, norm and magnitude and length all mean the same thing, so the length is 1 for a unit vector. And unit vectors are a lot of times nice to work with. So if v is not a unit vector, then you can find a unit vector u in the same direction of v by calculating u, it's just v divided by the length of v. So what we do is take that vector v and divide by its length, or its norm. And that will normalize the vector. It'll give you a vector in the same direction, but it'll just have a norm of 1, a length of 1. Let's look at an example. Our 3, 4 vector, we already know that it has a length of 5, as we calculated before. So if we scale the 3, 4 vector by 1/5, or in other words, take the 3, 4 vector and divide by its length, which is 5, then we get the vector 3/5, 4/5. So let's look at a graph of that. There's the vector v, and here's the vector u, 3/5, 4/5. It's in the same exact direction as v. It's just a scalar multiple of v, but it's a unit vector. Right? It has a norm of 1. V has been normalized to get our vector u. All right, another example of normalizing a vector. If you have v being 1, 2, 3, 4, we already figured out its length was square root of 30. So take your vector 1, 2, 3, 4 and divide it by square root of 30. So multiply every single entry in the vector by 1 over square root of 30. And that is a vector in the same direction. I can't graph it here because it's a 4-dimensional vector, but it's in the same direction, but it has a length of 1. You could double check, right? You could do it, the dot product with itself, and take the square root, you'll see the length is 1. All right, now we can try to compute the distance between vectors. So the distance between two vectors in n-dimensional space, the way we denote that is d parentheses u comma v. Okay, so that's just the way we denote the distance between u and v. The way you calculate it is you subtract v from u, so you do u minus v, and then find the length of that result. In other words, the norm or the magnitude of that result in vector after you've done u minus v. Now we'll see why that is the way to calculate the distance and make sure it matches up with our intuition. So let's look at an example. If our vector u is 0, 2, and our vector v is -3, -2, then the calculation goes, we'll do u minus v. That gives you 3, 4 when you subtract the two vectors, right? Because 0 minus -3 is 3, 2 minus -2 is 4. And then we find the length of that result. The length of 3, 4 is 5. Now, why does this work? Let's look at a graph and plot u and v. And the distance between u and v, right, the distance between those 2 points, 0, 2, and -3, -2, is that length shown with the black arrow. Okay, so what is the length of that black arrow? Well, notice that black arrow forms the diagonal of the parallelogram formed by u and v. And let me plot negative v, and let's just shift that parallelogram over. Right, so those are the same two parallelograms, and finding the length between u and v would be equivalent to finding that length, which is still the diagonal of that new parallelogram. But notice, remember from vector-vector addition, that black arrow, the new one, is u plus -v, right, from vector-vector addition. So finding the distance between u and v is the same calculation as finding the length of u plus -v, right? And that's where our definition comes from. We're finding the length or the norm of u minus v, which you can think of as u plus -v. So that's why this works. All right, so it'd be a good spot to stop and just think about why this calculation of the length of u minus v works. Let's see if especially with the graph, and make sure it makes sense there. Now we'll look at the orthogonality of vectors. Here, orthogonality you can think of as perpendicularity. So orthogonal and perpendicular mean the same thing, but orthogonal actually is a bit more general and broader of a concept, which we'll see later in the course. But for the purpose of this video, you can think of orthogonal as meaning perpendicular. All right. So if u and v are orthogonal, then the distance between u and v is the same as the distance between u and -v. So let's see why that's the case. The left picture is a picture of u and v being orthogonal. In the right picture, u and v are definitely not orthogonal. And notice that the distance between u and v and u and -v, right, where -v is just flipping v across the origin, scaling it by -1. Those two distances are exactly the same. Where in the not orthogonal case, the distance between u and v -v are different. Right, so this is a nice way to describe perpendicularity. We're using the word orthogonality. Noticing this truth about the length between u and v and u and -v. Right? They have to be the same for u and v to be perpendicular or orthogonal. All right, let's focus on the orthogonal case. So since those two distances need to be the same, we could also say the squared distances need to be the same. Right? So if the two distances are equal, then also their squared distances are equal. So you'll see why we're working with the squared distances in a moment. This will be a little bit easier to do the math. But we know the distance between u and v, right? That's defined as the length of u minus v. But since we're finding the squared distance, we have to square that length, right? So remember, we just defined the distance between u and v to be u minus v, and then the norm of that. Now we're squaring the distance, so we got to square that norm. All right, and then what we can do is write what that calculation would be, right? Because the norm of a vector is you dot the vector with itself. So the vector we're working with is u minus v. So we got a dot u minus v with itself. Remember, with the norm, or the length, you have to take the square root. But since we're squaring it, the square root and the square cancel each other out. So this is the computation for the distance squared now, u minus v dotted with u minus v. And with dot products, we can distribute, or you might think of the word FOIL, this dot product out. So we have u dot u, and we have minus v dotted with a minus v, which is just v dot v that we're adding. And then there's two different minus u dotted v's, right? There's a u dot minus v and a minus v dot u. Okay, so there's two of them. So that is the computation of that distance between u and v being squared. Remember, the length of u is the square root of u dot u, but since there's no square root here, that means it's the length of u squared. So we're going to rewrite u dot u as the length of u squared, and likewise with v dot v, to have this final description of the distance between u and v being squared. All right, now let's look at the distance between u and negative v, right? Because we want to compare the distance between u and v and u and negative v and make sure that they're the same. So very similar calculation, but now we're dealing with negative v. So the distance squared is u minus negative v, and we find the length of that and then square it, right? That would be the distance squared between u and negative v. And again, we can write that as a dot product between u plus v and u plus v, right? Because u minus negative v is just u plus v, and the length of that would be the square root of the dot product with itself, but since we're squaring it, the square root and the square cancel out. We can FOIL again, right? U dot u plus v dot v plus, now there's positive two u's dot v's. All right, and again, we can rewrite that in terms of the length of u squared plus the length of v squared plus 2u dot v. Now we did all that math for any vector u and v, right? We didn't assume that they're perpendicular or orthogonal, right? So we got these two results for the distance between u and v squared and the distance between u and negative v being squared. And so now this would be a great spot to stop the video and think about what must be true if u and v are orthogonal. In other words, what must be true if those two boxed in results are going to be equal? So what must be true for those two boxed in results to be equal? So think about what must be true there. Well, the answer is u dot v must be equal to 0, right? That's the only way those two distances will be the same, because if u dot v is equal to 0, then you have the length of u squared plus the length of v squared is both the distance between u and v, the squared distance, and also the squared distance of between the vectors u and negative v. Right? That's the only way those two boxed in results will be the same, is if u dot v is equal to 0. If it was anything other than 0, then you'd get different results for those two squared distances. All right, let's look at two examples to check to see if vectors are orthogonal. So are u and v orthogonal here? A good spot to check to see if we can figure that out. But for the first one, right, take the dot product between u and v. So 2 times 5 plus 3 times negative 3. Right, it'll be 10 minus 9. That's equal to 1. The dot product is not 0. So that means those squared distances between u and v and u and negative v are different, right? You don't get the same squared lengths and ultimately the same lengths between u and v and u and negative v. So that's because the dot product's not 0. Those two vectors are not orthogonal. Okay, the next example, do the dot product between u and v. You do get 0 in this case, and so that is orthogonal. Right? Those two vectors are orthogonal to each other, and the reason is the length between u and v and u and negative v are the same based on the previous math that we just did. All right, well, that's it for this video. Thank you.